Okay, yeah, I can invite you the link right now.
Yeah, so my email is
Yep.
SUMIT, my first name, then SENG@gmail.
Sumit.
SENG.
Oh.
SUMIT. SENG together at Gmail. I realized I just could have brought it. I had it in my home. I always leave it home. Send it?
Mm-hmm. Yeah, if you can join it, we can test to make sure that I'm gonna. So.
What your link? Yep,
yeah, how this is gonna work? It's basically it'll show up down here, and I'll just like click on you, and it should show up. So.
You're trying to hear me?
So. Yeah, how this is gonna work?
There's a lag.
Yeah, there should be. It's okay. Okay, welcome everyone. This is the first Cleveland AI Group meeting of the year. Thanks everyone for coming. I'm glad everyone showed up and hope you enjoyed the talks that we have planned. First one's going to be Intro to NLP by Sumit and Sengupta. Second's going to be Deep Learning for NLP by Andrew Plassard. And then I'll be talking about Deep Reinforcement Learning at NIPS 2017, which I was at in December. So we'll talk about it. First things first, I have some recent news slides up here. You can read through those. All this stuff is going to be on our GitHub, which there's a link in the About section of our Meetup group to that page, and I can send it out an email if people need it. Some upcoming events. Monday, I guess I'll just go through it. Monday, there's one at the Cleveland Clinic. Billy and I will be talking on machine learning, kind of similar to what we did for our first meeting, but we'll be slating it more towards healthcare. And I just found out that's open to the public. It's going to be at the Genomic Medicine Institute. So if anyone cares to show up to that, we'll be there. Yeah, they're going pretty quickly.
What time is that?
That's at noon.
Yeah. It's going to be linked to from the AI meetup page.
Yeah, so I'm hosting everything on GitHub, and and there's a link to that GitHub repository in the About section of the Meetup group page. So yeah, these are the events coming up. There's one on the 24th. The Cleveland R group, Tim Houlihan's going to be presenting on performance in R. Then there's a big data meetup. I don't think they have the lineup set up for that, but it'll be great, as it always is. And then the Cleveland Python user group, they will be meeting in early February before we meet again. So that's pretty much all I got for that. You all know the mission at this point, I think. If you haven't, it's in the the YouTube videos that we posted before, and it hasn't changed. So with that, I think we're going to get started with Sumit's talk on Intro to NLP.
Okay, can you hear me in the back? Fine. Okay, I don't need this. Thank you. So my name is Sumit Sengupta. I'm a cloud solution architect with Microsoft. What today, I guess in about next 30 minutes or so, we're going to talk about is Introduction to Natural Language Processing, NLP. This is not an excuse. When the last 25 minutes, we had a real scare. Like I had a Microsoft Surface machine, of course, and we realized that we couldn't plug it here for display. So I had to copy everything over in this machine. So PowerPoint we know will work, but I'm hoping the demo will work too, right? So with that, let's go to the next slide. So this is the rough agenda that we have. What is NLP? Text versus speech. So as in like when you type or going through a website versus when you speak into it. We'll talk about history and early use cases. We'll talk about applications of NLP, how it's being used. We'll show you some of the simple use case application that you can do. And of course, there's some use that you probably do in your home, like in your devices already. We'll talk about NLP using cloud tools. And finally, the demo god is happy. I guess we'll show you NLP using Python and NLTK toolkit as well, right? So natural language processing is all about machine learning. We're all familiar with machine learning. So basically, there are two kinds, well, I guess three, you can say, two kinds of machine learning, supervised and unsupervised, right? Supervised is simply you have a known variable and an unknown variable. So you're trying to predict what will be the impact of X over Y. Like if you think that wheat production only depends on rainfall, depending, how can I say if I had this much of rainfall, how much of it is going to wheat production, right? Simply as that. Unsupervised is when you have a whole bunch of set of data, you're trying to make some sense of the data, like how they fit together, how they cluster, whether 2 or 3 variables are playing together or not. There is another one, it's called reinforcement learning, which is basically saying that keep learning and keep trying until you hit the goal. A good example is let a mouse play in a square and trying to get to the piece of cheese, right? So until the mouse gets a hold of the cheese, it will keep running. So natural language processing is sort of mostly supervised because you know what you're trying to get, but a bit of unsupervised as well, in the sense sometimes language, being natural language, human language, is not definitive, is not pure science, right? We have multiple meanings and all that stuff. So the definition, I guess, if there is no official definition, but sort of that is analyze, understand, derive, express human language. So using machine learning to find insights and relationships in text, right? One of the key tasks, and we'll see in examples, is language detection. So if you just know what kind of language it is, just post a language and NLP will tell you what language it is. Then information retrieval and extraction. Information retrieval is like, let's say I send you an email, hey, do you want to meet for coffee at 10 a.m.? And if your email is really smart, it will take out the time 10 a.m. and automatically hold the calendar invitation block for 10 a.m., right? Versus extraction is get some summary kind of information, like get some meaningful, more than just a block of time, a phrase. Information summarization, talked about that already. Sentiment analysis is very common and very popular. So especially like public websites, Twitter and Facebook, you go through the feedbacks you receive for your product, for your movie, for a restaurant, right? And you try to get what is the positive and negative feedbacks you got. Machine translation, if anyone used Skype recently, is there a question? Okay, if anyone used Skype recently, there is a feature there that you can type in English and your friend somewhere around the world will automatically get it translated in a different language. And I tested it myself. It does a pretty good job, at least on simple translations. And the same thing, there's a Facebook post, right? If someone posted in a different language, even different script, you just hit translation, it will translate fairly good for you in English. Then there are other use cases. They detect malicious attacks like phishing or spam emails. Looking at the email content itself, sometimes you can tell whether it's real or coming from a real person or not. All right. So the history of the original history, kind of. Well, I guess in a way you can say history of all of AI goes back to the Turing experience and testing whether a computer can be smarter than a human being or not. But for NLP, most people agree that history started with these 3 people: Richard Brandler, Frank Pucelik, and John Grinder. They were like 3 people doing psychological analysis, and all they wanted to do is find out. Going through the medical records of 2 doctors, Dr. Virginia Satter and Dr. Fritz Perls. Both of them were very famous in what they did. They did 2 therapies and why they were so successful. So what they did was they went through the logs, the records, the conversations, and tried to figure out if there's a way they could figure out why these 2 doctors were so successful. So that was considered widely as the first of the NLP things. Oops, I did my. Okay, so different tasks. When I say tasks in NLP programming, in simple programming, or in applications, these are things that we do unknowingly, I guess, in our human conversation elsewhere. So tokenization is breaking text into sentences and then to words, so breaking words into parts of speech. Now, you might think that's a very easy task, and actually we'll talk a little later why it's not always very easy. Stemming and lemmatization. So stemming is like checking several words and going back to the roots of it, right? So several words have the same root, and they will mean the same thing. Lemmatization is on top of that, you add what parts of speech that word is. Then there's classification. So you go through a news site, blog site, and you figure out, okay, this is a sports article, or maybe it's a politics, maybe it's a review of something, that kind of stuff. You can optimize your search engines. You can do segmentation. So like I said, what is a sentence marker? When does an English sentence end? Well, if there's a question mark, exclamation mark, very likely that's the end of the statement, although not always with an exclamation mark. If there's a dot, you can have some word that has a word dot in it. So just looking at the character itself is not good enough to find out whether it's the end of sentence or not. Now, NLP can be a difficult task because for several reasons. One is that sometimes multiple words can have the same meaning, right? These are called homonyms in English. You got plenty of examples. I got two of them: address, as in postal address versus addressing an audience; tire, as in verb, or as in tire of vehicles. In English, they can have the same spelling and same meaning, so you really have to get the meaning from the context. As well as in some of the languages, like in Chinese, for example, it makes it easy in the sense the spelling is different if the word means the same thing, means the same thing. I mean, sorry, it means different things. But then you got this ambiguous headlines example. These are actually real headlines from a news article. Hospitals are sued by 7-feet doctors. Duh, what does it mean? The doctors were 7 feet tall, really? Well, what they actually meant by that was that 7 of the doctors sued the hospitals, right? Similarly, the next one does not say that teacher actually went and spanked children. It just happened that the teachers went on strike, and as a result, the kids were idle in their classroom. Well, you could argue the editorial board did not do a good job, but anyway, the NLP has to face through some languages. What's difficult is question answer. So if you want to find out, for example, whether this medicine is effective in treating the symptom, that's a real difficult task. I guess you're probably going to talk about some of the deep learning things. One of a good example use case of this deep learning is, I will encourage you when you get the slide to watch in this video, where actually they went and looked into medical publications and used NLP to track cancers in a way that the publications will tell you like what genes or sequence of genes are responsible for certain type of cancers. And then your blood report, you get certain kind of, I think it's called microRNA or something, and kind of match those and find out, how, and any of these, like any of the machine learning tasks, it'll tell you how successful it is, right? So split that into two, do a test, do training, all that stuff, and finally tell you that, okay, I'm successful in about 85 or 90% of the cases. Then creating a complete bot. I mean, it's okay to create a bot application where it's okay, what kind of insurance you want, card versus auto versus life, etc. But then when you go into deep conversations, it can become a difficult task, right? So it's a kind of two kinds of NLP, you can say. One is a classical, one is a deep. They're both very similar. I'm going to stay on the basic side, classical, of course. I think deep is something that he's going to talk about in the second one. But the main difference is that in the deep learning, they use deep learning models, versus where here what you're using is basic handmade rules, meaning some certain rules of languages, etc., and some statistical machine learning methods, right? So the applications for social media, information retrieval extraction, we talked about that. Summarization also, we talked about that. Another interesting thing is rumor detection. If you go through the messages and posts, people do talk about weird rumor messages. I heard about a thing like cancer is really not a disease; it's an it's a lack of something, some weird vitamin or something. I heard that. Adult content filtering, of course, not pictures, but just looking at the language, you can filter out the contents. Then trending topic detection. What are the topics that people are talking about, right? Sentiment detection will show you examples in the demo. And capture tweets in obsolete languages. That's very weird. There are languages that are dying, unfortunately, like many of them, like native Indian languages in this country. The thing about Twitter is open, like Tweets is an open database, like it's all out there. So you can actually go and scrape and find out some of this conversation that people may have tweeted sometimes. The challenge in social media are manifolds. When we have a document, when you write a real book or something, it's usually a single language, grammatically correct, right? There's no spelling errors. It's written in correct script. But in social media, of course, we have emojis, we have hashtags, people who are bilingual will probably mix up two languages, and of course, you have all kinds of typos and shortcuts, right? Then there are slangs. So if you have a thing called formality spectrum, like the language which is very, on the left-hand side is extremely colloquial, right? Casual speech, the thing that we talk, the thing that we will probably post in Facebook messages, such as chat and SMS messages. On the right-hand side is your extremely rigid and right language, legal documents, contractual documents, probably books that went through a good editorial review, etc. So here's some of the NLP example. Well, it's not just NLP, something else as well. NLP connected to the web, or to the cloud, right? So you talk to Apple Siri or Google device, Android device, or Microsoft Windows 10, Cortana. You tell, hey, Cortana, what's the weather in Cleveland this week? That's what I did. It answered, it understood my question, went to the web, put out the weather, right? Alexa, you tell Alexa, tell a joke. Alexa apparently got a sense of humor. Alexa can play music from your Pandora collection, right? What's the news? They're adding up to it, more and more. IBM Watson 6 years ago, 7 years, I guess, almost, was a Jeopardy champion. So there is online language translation. Go to Google or Microsoft website, it will automatically translate language. We'll see speech recognition, web search, and voice response. So one of the examples of speech recognition is you can actually tell your computer what to do. What if you're not good at typing, okay? So in Windows 10, in Mac, I'm sure in other devices as well, you can simply enable it to recognize your voice and do what it wanted to do. Okay, with that, how are we doing on time? 15 minutes?
Yeah, 17.
Okay, well, not bad. So this is the time to do for the demo. So in a typical, we'll show you demo in about two ways. One way is we will go to the web and cloud and actually run some there. We'll use Azure Cloud in my case. And the other thing is we'll show you some simple Python NLTK. NLTK is Natural Language Toolkit. That's the Python library for doing NLP applications. And we'll show you some very simple use cases for that. So you don't have to be a programmer. I myself is not a good programmer, but you can run those just straight off the notebook itself, the way I have it. Okay, so in this example, what we're going to do now is show you Microsoft Azure Cloud Text Analytics API. So that website that I have is a public website. You don't need to spend any money. You don't need any subscription or anything like that. Simply go to that website. And when I put on this tech, everyone enjoyed the Cleveland AI meeting. Hopefully it's true. It was an evening well spent. And then it comes out with analyzed text. So there's three things it's doing. It's detecting the language, English language with a certain amount of confidence. And a key phrase, so that you found out there are actually two key phrases, which is pretty good. There's a number, so more positive, more, it's higher the number. If it was critical, if it was bad, then it will be a lower number. And the text on JSON is versus the same thing, it just represented in a JSON structure. That's about it. So with that, I should be able to go to switch and go to, with Firefox, is it? That's Firefox. Yeah, there is that. Just this one.
Okay,
This
so
is
you're
fine.
gonna have to move it up to the screen.
Oh, how do you move it up? Sorry, a Mac challenge, at least at now. So, that's fine. Thank you. Okay. Okay, so I have to.
Sentiment is one to the left. The tab to the left. Okay, yeah, there you go.
All right. So you can get an Azure subscription for free. You can get a trial, get $200 credit and all that. I got my subscription, and here we are putting a key. So the key is just kind of like a password. And then what we did over here is go to the left. Put out 2 English sentences. So I told it it's an English language. I give an ID, which is nothing but a key, and then say that 2 words, which are some known phrases. Not my cup of tea. I was so touched by the movie that I started getting goosebumps all over my arms, right? So when it comes back, it says the sentiment is 23%. So the first one was pretty negative, right? What I said was, this is not my cup of tea, which is considered negative. Oops. What is that? What sentiment? Yeah. And then I was so touched by the movie that I started getting goosebumps. It's got a score of 26% as well. That's not something high. This should be high. That doesn't surprise. While I was doing the copy, I also had to copy every single statement I had. So I think I may have gotten the wrong statement. So let's open up another one. Oh, come on. Okay, so here's one. What a wonderful experience. The rooms were wonderful. The staff was helpful. Today it was warm over here. Again, it's an English language. Detect the key phrases, and the sentiment is 96%. So let's do this. Oh, what is the language? Oh, I don't have that one. Anyway, so I don't have that right now, but there's another one where you can actually type languages written in different scripts. So it's not in Roman script. It could be Chinese. It could be some European. It could be some Asian languages, and it will detect you the language again with a certain amount of confidence, right? Okay, so with that, let's jump over to some of the Python NLTK thing. So that will be, yeah. All right. So ignore the first top part of it. This is for your environment check. You probably don't need to do that. The NLTK library, if you want to download it, the easiest way to do it is just install like Anaconda, right? Which comes with its own Python, which comes with NLTK itself. So when you say import NLTK, it's going to import NLTK package. I do the shift and return, right? Oh, why? It will take some time. Will it pop up? Oh yeah, it did here. Book. Okay, it's going to take some time. It over here on this window.
Oh, I see.
In the book. So what it's doing is it's doing all the books, downloading a whole bunch of books. So NLTK has got a lot of data itself. It has one of the interesting it has is actually it has 9 books. That's just with download. It's going to take some time. Oh God, we don't have good speed over here. There is also presidential speeches going back to I don't know what time, but up to 2009. They haven't got to 2013 yet. So you can actually go through those and do some analysis. Well, this is taking some time. Let me see what I can do in my notebook, which is, let's see, let's do this one. This doesn't make anything. here, this is an example, right? I said time to get started with NLP hands-on in Cleveland AI Meetup. Python makes this real easy. We lucked out with weather, trust me on that. So what we're going to do is, this does not read any data to download. So this is the data I'm feeding, right? Let's do only this much. Shift. Okay. I guess it's hung on that one still. Oops, what happened? It's probably still doing the download. We can see if the download's still working. Probably it doesn't. Okay, well, in the interest of time, what this is supposed to do, it may be stuck to the book download still. I don't see it coming up back here. Is it'll break up this whole structure into different sentences. So what this will come back with is a separate sentences. So it will say these are 3 different sentences. Similarly, this will break it up to different words. It will say what the words are. And this will tell you what the parts of speech are. And when I say parts of speech, NLTK and NLP does parts of speech more than we do in English grammar, in the sense that it's not just verb and noun and adjectives and like that, right? It actually has a lot more classifications of that. And if this thing comes back, then this will show you, for example, JJ is a parts of speech and what it really means, right? Let me see if it came back. No, it didn't come back, I guess. Try it again. So shift, return. Okay, there you go. So you got the 3 sentences, right? So now, if you do the words, the tags also. Uh-oh. Are you comment out the import statement?
Yeah, comment that up and then
Oh, which import? Oh, this one? Okay.
the bottom one.
Yeah.
And then run it again. There you go.
Okay, so they broke it up to basically individual words. Now, you'll notice one thing that NLP considers dot as a word as well. Even punctuation is a word as well. So, well, that's the way it is. Then let's do the import. And then let's do the tags. Let's see what tags they are. Running still. Oh, there you go. So that's the parts of speech. Like I was saying, the parts of speech are more than what English does. So these are different parts of speech, which of course, I don't know what they mean. So the one way to find out is, let's find out what the JJ parts of speech mean, right? Adjective or numeral, ordinal. So get some examples. That's all adjectives, ordinals, etc. And it's funny thing is that it can make up fairly complicated adjectives as adjectives, right? There are a couple of examples I guess I will show you, then I will pause for, well, what? If the books are not loaded, so I guess I'll skip that. Oh, maybe it is. Let's try the book. So this is all about the books. So I will try if the books are loaded or not. No, it's not, unfortunately. So these will not run. So if the books would have been loaded, what you would have seen is this will give you like searching for this particular string in all the books. So all the lines, it's like a grep in Unix grep, if you're familiar with that. All the lines that has that word. The similar is actually interesting in the sense that it's not synonym to the word, but in that document, in that context, what that increase really means. So text 7 in this case is a book. It's one of those books that, essentially I'm hung up trying to download. This frequency distribution is another interesting thing. Is it will tell you like the frequency distribution, which is statistical fixed, how many, like each word, how many times it occurs in the document, right? And it's just a number, but then when you plot it, it gets really interesting. So you can see like what is the most 30 common used words, how many times it appears, right? Then you can do a frequency distribution, which will look like a curve like that. You'll see like most 30 words, if you keep on adding them, they will probably be like 40, 50% or 20% of the whole document, right? So that's one thing. Now, these are all still statistical analysis. This dispersion plot is interesting. Like, so what it will do is it'll go to the book, read for this string. It will tell you where the string actually is located in the book. So for example, is it in the beginning? Is it in the end? Is it middle? So you can kind of see where this is discussed. I don't have it here. There's a function called hipax, which actually tell you the opposite, which words are rarely used, like only once or twice, right? So that kind of stuff. There's things you could do yourself, very interesting, like URL lib. So this is a package for URL lib to access URLs. And if you have a URL website, this particular one is actually just a bunch of 4 text. All this does is basically goes to the website and prints out the page, right? And you can do other things, again, word parsing, word tokenization, some limitization, etc. With that, unless I can make my other Azure demo working, I guess I will conclude my talk, and I will wait for any questions if you have. No? It was too good or too bad? Oh, yes, there you go.
How does Microsoft's hybrid system with Amazon's?
Oh boy, I think we're not allowed to discuss that. I mean, let's talk really essentially offline. I mean, quite frankly, Amazon, Microsoft, and Google, they're always trying to play catch up with each other, right? If there is a competitive advantage of one over the other, but usually the other company tries to catch up with that. As far as NLP goes, I know we have the 3 things I showed you: language detection, phrase detection, sentiment analysis, etc. I've seen customers and partners, when they decide, ultimately sometimes it comes down to cost, how much it costs to run the same thing. And at the end of the day, most companies like to work with multiple cloud vendors anyway, which is probably a good thing. Yes, sir.
Thank you so much. This is great for introduction for someone like me who's working with So my question is, this specific package or any of the packages that are widely available, is it focused on what you would see on social media? Obviously, this is a big area. How does it perform when it comes to subspecialties? I'm in healthcare. I want to use this to scan patient charts and come up with, models, or legal, or science, or any of these subspecialties where the language is not the same as what you would see on the internet.
Yeah. So if you're in healthcare, I will really encourage you, when you get the slide, to go back to the one of the links I have is a video where they talk about how NLP was used to detect cancer. I don't know if you're at the beginning of the talk, we talked about that. They have actually a tool which can be used by multiple people to do similar research, where you can give it a set of documents and you can see what you're looking for. It will see how many times the document is. I mean, you should really watch it. It's about 20-25 minutes. It's not too long. It's open public. Answering your question directly, I don't know exactly if Python has specific packages for looking into specific type of data. But like I said, that tool that they came up with, I know it's made public. So you can use that.
I think the question he was asking is there any capability that domain specific vocabulary?
is the answer. Okay. Probably there might be. I don't know. Yes, sir.
Here's another way to put that question. Does it work with ontological hierarchies like the site project?
Oh, what hierarchy, sorry?
Ontological, like semantic, the type of thing that was popular several years ago, so-called semantic.
There might be industry-specific or vertical-specific vocabulary that are put out there. I don't know. The NLP examples I was going to show you here, books, and they have writers, newsfeed, they have corpus Brown, which is basically a collection of million words, I think. Brown dictionary or something that was started in 1960s.
So by ontological hierarchy, do you mean like a semantic hierarchy where you break down a sentence into like a word tree or a sentence tree?
Or a concept tree.
But it's not just about the
You got the old style.
What, semantic?
Yeah, semantic, yes.
Yeah, well, they still use that now. A lot of times that can give you increased performance on things like sentiment analysis or translation, things like that. But I'm not sure if they have that. I'm stumped, honestly. I guess we'll have to look it up.
We should probably keep the questions in the meta group and try to get answers.
Yeah, we should.
Yes.
Yeah, do that, yeah.
Anything else? Oh, wow.
I think we have time for one more, and then we'll move on.
Oops, sorry. Yes.
I was just going to ask if you think there's a significant advantage to using GPU-based deep learning strategies for classification as opposed to
Yes and yes. So if you use GPU, the case I kept talking about, the cancer detection one, they actually use GPU models to do that. Yes, of course. When you have a lot of data to process, you want to get things done quicker, you want to do things faster, you need those GPU processing. So there's, I mean, this was running in, well, right now it's on Mac, but my one Windows machine, so it's a small set of data. But yes, depending on your volume of data and what task you're doing, and also the other thing is how quickly you want to get in.
what if you're not concerned about time? Classification.
Depends on how long that time is. If it's over your lifetime, you might not. Yeah, I mean, if it's a few hours versus 2 seconds, yeah, sure, why not? Yeah.
In general, GPUs only speed up the computation. It doesn't change the actual algorithm. In general, although if you distribute things like on multiple GPUs versus multiple CPUs, that can have an effect. But how you distribute it. But in general, GPUs only speed up computation when you can parallelize that computation efficiently. That's what GPUs are used for.
So do you think that boosting could potentially have, let's say you're looking to kind of like a mid-range project, are you not too worried about speed? Boosting could have classification and accuracy advantages over learning?
The only classification accuracy advantage that you're going to get is the ability to iterate on your experiments more quickly with your experiment. The actual running it on GPUs will not impact classification.
I'm just saying, like for those GPUs, just looking at the
versus deep learning. It depends on the situation. I think I'm just going to talk about that next. So.
Yeah, and GPUs could be expensive, so that's the other thing you have to consider. So, well, thank you very much. He just installed. It knows why we're done. Oh, sorry.
Why not you do that? Okay, this is Andrew. He will introduce himself.
Hi, everyone. I'm Andrew. First, thanks for all coming out. I'm a Progressive employee, and we really appreciate all of you coming out here to see the talks today and to be a part of the meetup. A little bit about me. Recently, I finished up a PhD in applying deep learning to brain imaging down at Vanderbilt. Now I'm a data scientist here at Progressive, and I teach over at Case. So we just had a really great talk on what NLP is, and a lot of these topics were covered. Text classification, what is the sentiment of a tweet, question answering, caption generation. Take a photo and what is the proper caption for that photo. At its core, NLP is teaching machines to read and write, and that's kind of the deepest simplification I can have for that topic. So I think it's really interesting to compare and contrast image processing to NLP. 2 months ago, when this meetup group met, we had a few great talks on image processing, and images are where my heart is. This is where I came from, and the ImageNet task is one of the classic image processing tasks. In this case, they have 1.2 million training photos and 100,000 testing photos, and these photos are classified into 1,000 different object categories. And the goal is to take this photo, and each photo is 224 by 224 pixels, and then pick out the best class out of those 1,000 categories for what's in that photo. So for instance, the second photo from the top is a container ship, and looks like the net got it right. There's a leopard over there, and these are the kind of things that the ImageNet task is doing. On the other side, NLP is looking at tasks like machine translation. So this is a little thing that I did using Google Translate, where we say this is a test of machine translation, and it translates it into some Spanish sentence that I can't read. But the big difference here, in my mind, is for a task like machine translation or sentiment analysis or caption generation, there's not necessarily that same fixed input and fixed output that's present in an image processing task. Here we need to go from a list of words that are in a row and produce a separate list of words. There's not a guarantee there's the same number of words in the input and the output, and there's not a guarantee that there's a direct correspondence between them. And this is a real challenge. This is getting into the classical idea of machine learning and statistics. Data scientists, we like our data in spreadsheets, where we have features in columns, and these features are meaningful in some way. For instance, here we have two features, feature 1 and feature 2, and the goal is to build a hyperplanar to classify the green and red data from each other. And we have a lot of really great machine learning tools available to us to draw the lines to separate these groups. You can see two examples in B and C, using a support vector machine and a support vector machine with a kernel. And this is classical machine learning. We've been doing this for decades now. And we're pretty good when we have a spreadsheet of information and we're trying to predict one fixed output. But that's not regularly the case in NLP tasks like we saw in the previous talk. So what I'm going to be talking about today, first I'm going to go through an example NLP task and what it is, what we're looking for in it. Then I'm going to go through the classical approach, the approach that if you were a data scientist 15 years ago, what you would have done. Then I'm going to go through a kind of modern deep learning based approach for the same application. And then I'm going to talk about something completely unrelated because I have a platform right now. And so just as a goal though, my goal here is to give you an idea of how an NLP application is set up, not to give you the nuts and bolts inside the programming. I actually did the application I'm going to go through right now. All the data, all the work for it, I did myself, and I have an IPython notebooks like the one we saw a few minutes ago that I'm going to clean up and get to JSON for all of you to see and work with. But my goal is to give you an idea of how to look at your text data and to work with your text data into producing an output that is of interest to you. So the task that we're looking at is sentiment analysis. This is something we just heard quite a bit about, and in particular, sentiment analysis on Yelp. So if you've ever been on Yelp, you're going to find a lot of text reviews and then stars associated with them. In this case, this is a person reviewing their favorite Thai place of all time, and they gave it a 5-star review. That's a really positive review for that restaurant, and that's awesome. And the goal of this is to take the review text as an input. So my favorite Thai of all the places, etc., and then produce the output number of stars using that input text. So take that text review and produce the number of stars that it got. And this is an interesting task because even though this is data particular to Yelp, sentiment is something we see in text all the time, and it's really valuable to go through and be able to monitor that and to understand the sentiment of a review or text or anything else that you're working with. So a little bit more about the data. Yelp actually has an amazing data set out there available for the public. There's data there's review data, there's data about the business locations, there's photos, and there's a bunch of different cities that they have data curated for. For the purposes of this, we're going to be working with the 4,700,000, which that's a ton of data. So if you've ever wanted a really large text data source to work with, I highly recommend working with this one because the data is really, really good, and there's a lot of interesting signal in this data set. Just to give you an example of what one piece of data looks like here, this is one review. All the data is coded in JSON like this, but you can see in the middle there's the text, and a little bit above it there's the number of stars associated with that review. This is a really great review. If I had a restaurant, this is what I want my reviews to look like. So, but our goal, once again, is take that text and then to predict that number of stars. So all this work was done using Python, and then a list of libraries I have up there. NumPy is just like a matrix math library. NLTK we've already talked about. Scikit-learn is a fantastic machine learning library. And then PyTorch is my deep learning tool of choice, which I'll go into that a little bit more later on. And then Matplotlib I just used to make some figures. So what I did is I took those 4.7 million reviews and I picked 2,000 1-star reviews, 2,000 2-star reviews, etc., up to 5-star reviews, just to get a balanced data set. And then I did that for the training data and the testing data. And so what that means is we have the data broken into two pieces. The training data is the data we're going to be building our models on. So we're going to be using that data to build our models and train them and do whatever else we need to with them. And then the testing data, we're never going to touch in our processing. The testing data is completely held out, and we use that testing data to evaluate how well our model actually worked. And the reason we do this is because a lot of these machine learning approaches can fit to your training data better than they'll extrapolate to your actual data that you get in every day. So this is a really common practice, and if you're doing any machine learning application, this should be one of the first things you do is divide your data into a working set, your training data, and then a testing set that never sees your models until the evaluation time. So the first thing we did in our classical approach is that exact same tokenization step that we talked about previously. We took this data, and then we broke the text down into tokens. Here, the tokens look like killer, work, out, period. Owner of Vlasta is awesome. Exclamation point. 30 minutes, wham, bam. And so we did this for every single one of our reviews. And then what we did is we selected the 2,000 most commonly occurring words in the data set. And I think this might get to some of the questions that were asked in between. For a lot of machine learning and natural language processing applications, you're going to go through and redefine your language corpus or your set of words based on what the application you're working on is. So in this case, we found the 2,000 most commonly occurring words. And then for each review, for each of our 10,000 training examples, we went through and counted how many times each word occurred. So I'm pretty sure the first column is an exclamation point or a period. So that's the count of times a period occurred. Then the count of times the word the occurred, etc., up for our 2,000 words. And then the final column is just the number of uncategorized words in that review. And so this gets back to, this basically is a set of features, which is our spreadsheet of information that we like, that I mentioned previously, where each of these features is identical for each and every review, or what each feature column means is identical for each and every review. And then we have our outcomes, which is still our star ratings. So our features are fixed and a really consistent and fixed set of information. And then our outcomes are the number of stars that our review got. And like I mentioned, this fits really well back into our previous mindset of having a fixed set of features and a fixed set of outcomes. This is exactly like all previous machine learning applications. And so this works really well as an input to classical approaches. So I chose a random forest for this approach, but basically you could choose any regression technique that you wanted, given that sort of input data and the outputs that we're working on. But what a random forest does is it basically subdivides our data into smaller groups, lots and lots and lots of times, and then we can average those groups together for a given case. But how this works isn't that overall important to the goal of this talk. And so what this is the results. Like I said, I actually went through and did this. So for each of the true scores, which are listed along the bottom, I went through and then grabbed every result for the true score that we estimated for it. So you can see that there is a correlation between the estimated score and the true score. The actual correlation is 0.358, and on average, our absolute error is about 0.9. So on average, we're less than 1 star away from the correct star value for each case. So that's actually pretty promising. Saying that we're within 1 star is pretty good. And this is kind of our baseline approach. So even though I am a deep learning person also, I think it's incredibly valuable to have this sort of an approach where we baseline our results based on previous work. So this is the kind of classical approach. Now moving forwards 7 or 10 years from when that work was kind of beginning. This is getting to the modern approach. And I stole this slide from that presentation listed there. It's a great presentation. I really recommend going through and taking a look at it if you're interested. But this is kind of the more modern approach of how natural language processing is done. So it starts out exactly the same. We take our input, tokenize it into pieces, and then what we do is we assign a number for each word in our tokens, or each symbol in our tokens. And this is basically an index into our data. And then what we do is we look up an embedding for this data. And I'm going to cover what an embedding is in just a second, but it's really not important to the overall goal of this talk. But this is basically really similar to our previous approach, but we're not combining anything together yet. Just briefly on an embedding, what an embedding is it's a way to structure your data that has a little bit more information about it. Saying man is word number 1 in our data set and woman is word number 7012 in our data set. There's no information that really joins them, but the embedding is a different sort of space that has related information about them. And this is probably the most complicated thing I'm going to talk about today. So I hope you ignore everything I'm saying right now, because it's really not important to understanding what I'm getting at. But the next step is our recurrent neural network. And this gets into deep learning. So in a recurrent neural network, what we have is we have an input and an output. Once again, our input is our text, and our output is going to be our sentiment. So what we do is we'll process some input into a hidden layer, and that'll pass to an output. What's different about our recurrent neural network is it will also pass some information on to another state, which will pass some information on to another state, to another state, to another state, all the way to the end of the network. And this idea of recurrence, or recurrent neural network, says we have an input, and that has some information. We're going to pass some information about that input to the next state of the model, and then to the next state of the model, and then to the next state of the model. And then for sentiment analysis, our inputs here are the text. So the way the recurrent neural network will see the text is it will read the word that. That will get passed through the hidden information. Some of that hidden information will get passed on to the neural network, which will then read the word was, which will pass on that information to the word and et cetera, et cetera, et cetera. For sentiment analysis, we can ignore everything until the very output. And then hopefully, this is a positive result for our network, because that was a very good movie, is a positive sentiment sentence. But this idea of passing information from one layer to another is the core of recurrent neural networks. It's what really differentiates them from a lot of previous machine learning techniques, because this neural network here does not have a fixed length. This could have kept going on and on and on and on, and then read the information as long as we wanted it to. So I went through and trained up that exact neural network using PyTorch, like I mentioned before, on that sentiment analysis task. And this is about the result we got. And then to compare the random forest and the RNN, we see the RNN, the correlation value is dramatically higher, and the error is down to 0.6, which is a pretty dramatic drop from the 0.9. If this is a little bit confusing, just know the RNN did a lot better than the random forest. And this is a really basic RNN that I trained here. Looking back at this RNN right here was trained on those 10,000 examples for 24 hours on a laptop I bought in 2013. And so this worked really, really well, like much better than I thought it would in reality, because that's commodity hardware, and it wasn't all that much data with only 10,000 examples. So a really simple application. This worked surprisingly well. Yes?
Are those scores on your test set or the training set?
Test set. These are all test set scores. Great question. I never actually look at the training set scores because, well, except for seeing how far apart the test and training set data is to see how overfit it is. But for this case, test data, not too bad.
Did you use a validation set too? Did you really stop them?
No, I didn't go into anything like that. I actually did trial that just for my own purposes, just with a super fancy model and all that, and it got a lot better than this even, which is cool. But I didn't go into any of that for this purpose because I just wanted to do the simplest possible.
I didn't see the scores. What's that? Could you go back one slide? No, one more before that. When you talk about this, was the 5 or 4 or 3 also one of the inputs? I mean, I don't see it there.
Oh, right. So this is great. Great question. So that's the output of the model. So in this case, I just used a plus sign. For that case, this would be maybe a 5-star review from the Yelp sense. But that's the idea, is that's the output of what it's predicting, is that 1, 2, 3, 4, 5.
Okay, but Okay, you say you trained it for, some period of time.
Mhm.
One of the inputs was the score given by the human?
Oh yeah. So in training, what we do is we give the network all this information.
Mhm.
We tell the network, predict whatever you want to predict what you think the score is.
Mhm.
And then we say, okay, here's what our score was, and here's what your score was. Here's the difference. Get better at what you're doing. Improve yourself.
That on a per review basis.
Per review basis. Yeah.
Right, so one of the inputs, there's a comparative that loops back or something.
That's the training part of the data. And
Okay.
yeah, then over here, this is our testing data though that never saw that testing data never saw the result. Okay. Any more questions about this?
I don't understand the dots.
Oh, great. So these are just box plots. Dots are just the outlier data points in this sense. They're just mathematical outliers by the definition of a box plot. I box plotted them instead of doing anything else because it was a more effective way of bidding the data than just putting a bunch of scatter plots up there, since everything's kind of clustered in certain columns.
I have a question. How do you compare? So when you mark a star as a human being, right? You have 5 stars out of it. I mean, I might give a great text review, but I would still give a 4-star.
Mm-hmm.
So how is that going to compare with your result?
Right. So the network might get that wrong. If you give the most glowing review possible and then you give it 4 stars, the network will probably get that wrong. You're right. It's only as good as what it knows. And if it knows that this is the best experience I've ever had, is a 5-star, but you give it a 4-star, it's going to get some wrong. So it's just doing its best to predict what it thinks your result is based on what it's seen previously.
Do you random search or grid search for your hyperparameter?
Nope, I just did something really simple. Really, I just wanted to get one example done using my kind of old laptop. So I didn't do anything fancy to get this result at all. Anything else about this?
Did you do any sort of pre-processing on the data?
The only pre-processing I did was that tokenization step, where I just broke the data down into its tokens, and then I selected only the top 2,000 words or so. That's all the pre-processing I really did for this. And I also made sure my training set was balanced across the scores, because this is a little bit of a skew distribution. But that was the extent of it. Yeah.
Is there any reason you went with neural net as opposed to
I mean, going back here, I tried the random forest approach, which, random forests are kind of correlated to GBMs in a lot of ways. They're not the same, obviously, but random forests, I like them more for various reasons. So I could have just easily plugged GBMs in for this. But I just used random forests because I like them. But yeah, my point of this part with the random forest was to say you could plug whatever machine learning approach you want in for here. Random forests are the least important part of it. This is just to get my baseline of something previous or an older approach.
So I heard that the package, Green actually has patient accuracy. That's what it's one of the most highly sought after.
Yeah, XGBoost is really cool.
What was the question?
Okay, great. So the question is about a separate library or a separate algorithm called extreme gradient boosting, or XGBoost. And XGBoost is probably the cool thing to do right now if you're doing a Kaggle competition, which Kaggle competition are these really large, openly available data science competitions, essentially. And XGBoosting is one of the cool approaches. And I'm not going to get into the math of how XGBoosting works, but basically it works really, really well when you have medium-sized data. So if your data set is 50 to 1,000 data points, you want linear regression or something simple. If your data set is 1,000 to points, XGBoost is going to be the tool for you for a lot of cases. And if your data set's 50,000 or more data points, you got to kind of go to deep learning. So what tool works best is really a function of what your problem is, one, and how large your data set is, two. The one real advantage that neural networks have on this NLP task right here is they can model the structure of your input, right? The deep net will read your text from start to finish, whereas the other approach that I described, you lose all the information about what words are next to each other and things like that. So an approach like a random forest or a GBM or XGBoost or whatever else loses the structural set ordering of the words that I think is super important in this task. Yeah.
You would expect
only a certain category for the reviews, right? Only reviewing restaurants, only reviewing gyms.
Absolutely. I mean, the more specialized you make your task, the better results you generally get. But also, if you have a big enough network or a big enough learner, you can kind of get away from that for the most part. Anyways, I'm going to talk about one other thing, and this is a really important NIPS talk. So Jason can talk about NIPS a lot in a minute, but this talk was really, really important to me, and you can find the link right here. But it talks about social biases in machine learning. So as a person who likes statistics, when I think of biases, this is what I think about usually. This is the first thing that comes to my mind, either model. But this is not what this talk is about. This talk is about social biases. So Turkish, this is an example taken directly from her talk. I hope you guys all go and watch this talk because she does a much, much better job of talking about this than I can. Turkish as a language does not have gendered pronouns. So translating he is a nurse or she is a doctor, which is what I do, what's happening on the top, gets those two results. So the letter O is the non-gendered pronoun for he/she. And I'm not an expert in Turkish, so I'm not going to. Right. So fantastic. But what this gets really problematic because on the bottom, we take those two translated phrases, which translated he is a nurse and she is a doctor, and we translate them back into English, and we get the result she is a nurse and he is a doctor. I don't think this is funny. Like, no, I'm serious. This is a real problem because encoded in a lot of our machine learning techniques and all of our data sets, there are gender biases like this and so many others. And there's been a lot of examples in the news lately. So whenever you or anyone else are working with machine learning tools like these, I really hope you consider these sorts of biases in what you're doing. And I hope you guys watch Kate's talk because it was a fantastic talk.
There is a TED talk about a Stanford PhD grad and a postgraduate student. She talked about that as well. She's like an African-American woman. She was talking about real biases in machine learning.
Yeah, I'll try and find that and add it into this talk because this is a real important problem. And I'm not going to harp on it anymore because the talk does much better than I possibly can with this topic. So please go take a look at that. And with that, I'd like to open up to any more questions. We already covered a lot of questions, but if there's anything else NLP related or deep learning or anything else that is interesting, I'm happy to answer questions. Yes. I think so. Several advantages to Python over R. First is I know Python, and I'm a terrible R programmer, so that's the first one for it. But I think right now Python has a lot of the best libraries available. For instance, all of this uses PyTorch, which is a fantastic library for deep learning. And I'm sure there are ports of PyTorch to R, but they're never going to be as good as the Python version, at least in my experience. Also, Python is just better for working with large streams of information from multiple sources, and it's more flexible in terms of the tools available for working with data from multiple venues and multiple types of data and different structures of data. So I've personally found it to be just a significantly easier tool to work with from a just computer science programming standpoint. Yeah.
Is deep learning the best way to do nonlinear regression? Is part of the job?
So my PhD is in deep learning. So I'm probably not the best person to ask, but I think the answer is no. So the question is deep learning the best way to do nonlinear regression? I think the answer is no, but it's really context dependent. So it's impossible to answer that without a little bit more information about the context. I don't remember.
Okay, so there's something called the no free lunch theorem. It was a mathematical result that was proven maybe 10 years ago, something about it was trying to find a particular class of algorithms, optimization algorithms that would do the best on like all tasks. And what it found was that you actually can't find that class. It means that all algorithms on average over all possible tasks do exactly the same. So like you said, when you're saying, does this algorithm do better? It's all about what the task is. And some algorithms do better on these tasks, while others will perform very poorly. But then those that perform poorly on that task will be superior on a different task. So it requires experience, and it is a little bit more complicated than that one's the best and that one's the worst.
And I'll also say training up deep nets is much harder than any of the other machine learning applications available. So Training up that random forest to do that, I got that to work in like 15 minutes. Training up the deep net took like a day of training for that, and like more time just fiddling with it and making the parameters work and getting all the training schemes to work. So even though the deep net worked better for this case, the random forest was a lot easier. So it's very context dependent. Is there a second part two?
Well, I think you partly answered part two, but part two was going to be, what else does deep learning give us other than creativity?
So deep learning, what I think really is valuable about it compared with other approaches is it's great at modeling spatial information. And spatial information I see in two major contexts. First is this text example, where the ordering of text is very, very important, and our ability to model that is limited by other approaches. And second, in images, it's really, really great. Because it's fantastic in images because images encode so much of the spatial information, and just based on the fact that pixels are all next to each other. And the deep learning is able to work with those pixels, and then most important to that classification task or regression task or whatever else, without me as the programmer ever having to go through and say, this is what we're looking for in the photo. So in those kind of contexts where there's a lot of joint information in the features, and it's hard to model that joint information with other approaches, I think deep learning is a fantastic approach for those situations. Does that answer your question?
Yeah, there's a third part.
Absolutely. Those are great questions.
How is it computer science got ahead of the mathematician, figuring out better ways to do various types of plot that would have been figured out by mathematicians back?
So that's an interesting question. Well, yeah, but I think getting to the core of that is, I think a lot of machine learning is kind of getting away from pure math, and it's getting closer to the intersection of computer science and math. For instance, all this deep learning stuff, we could have done this 30, 40 years ago had we had the computational and data sets available, computational things and data sets available to us. The original paper on how to train a neural network was written in 1986. And really, we haven't learned that much since then. All these advances a lot of them are due to our computational ability and our data sets that are available. So this is still a mathematical thing, but it's just leveraging our current abilities with computers that we have, in my opinion. Other people may disagree with me on that, but is that the wrap-up music? So that's my take on it. Yeah.
Can you talk about more about the size of data and what kind of algorithms or models we're looking for?
So yes and no. Yes, in the sense of like I have general mindsets of what size of data you need for different approaches, but I don't have any like real mathematical thing to back up, saying, okay, you need 50,000 examples to do deep learning. Like during my PhD, when I was working on brain imaging, I was working on 5,000 examples. Trying to go back a million slides here. When I was looking at brain images like that, I had 5,000 examples, but there's so much spatial information and so much like extra information that we get with deep learning that we can't capture with classical approaches for working with that data, that 5,000 examples was enough. But it's application dependent. It's hard to make generalizations, and I don't really feel comfortable making generalizations because I don't know what you're working with. I don't know what you have available to you, and I don't have your data in front of me.
Also depends on how noisy the data is.
Absolutely. This data is pristine and beautiful. Your data might not be, or your data might have other challenges that are really difficult to work with. And so there are other limitations that you need to be aware of and understand, which is why I think baselining with things like this random forest approach is really, really valuable, because that gets you an idea of how well you should at least be able to deal with deep learning if your application is appropriate for deep learning.
What are your recommendations for specific packages?
Ooh. Unsupervised learning in text, that's hard. I don't have any answers for that. I got nothing for you. I'm sorry.
If you're doing like topic classification, or like topic clustering, you want to check out LBA.
Oh yeah, latent. Oh, LDA as SVD. Something. The truncated SVD, LDA. It just depends what your application is.
If you're doing speaker extraction from images, you'll want to look at the pre-trained networks that are available. And I found I was pretty good with that. There's a lot of positives online where people have trained large images on images, large classification. You can transfer those over. I would go with that. But I'm biased.
Conjecture I had back in the days when neural nets were first becoming popular, and they were being used to control the quality of washing with washing machines, was that the neural nets are particularly useful when there's an underlying physical model, and where a picture is a physical model, an additional physical model, and their performance deteriorates as the domain becomes less and less concrete and more abstract. Relative to, taking seismic readings and figuring out where the oil is going to be easier than,
Yeah, I think the point is neural networks are really great when there's a lot of correlated information in your data, because it's good at extracting what's important from that correlated information. Make too many assumptions or bad decisions based on your data. But anyways, that was the wrap-up music for me. So thank you all.
Oh, you dropped something.
That's not unusual.
All right, let's take a vote. Do we want to take like a 5-10 minute break, or do we want to just keep going? Keep going. All right, we'll keep going. It's gonna take me a moment to get up set up. Oh no. Excuse me. No one steal my password. One more. Okay. Oh wait, no, that comes next.
Do a show password.
All right. I think that's how you do it. Yeah, there it is. Okay. All right. Yeah, so I'm Jason Mancuso, the organizer of this meetup. I've given my introduction before, but I'm a data scientist at Pandata, graduated from John Carroll, studied math, did some machine learning at the Cleveland Clinic a little bit, and now I do research in my spare time with AI. And I'm talking about a research conference that I went to called NIPS. It's the Neural Information Processing Systems Conference. It was in Long Beach from December 3rd through 10th. And it covered both biological and artificial neural systems, but it now mostly focuses on artificial because of the attraction that it's gotten from the tech industry. And this growth, so right here we have a graph of the attendance of NIPS over the past few years. It has grown exponentially. It continued that this year, and that's in large part due to hype around AI. Stats from this year, this year we had 7,500 to 8,000 attendees, so that kept bumping up. 1.8 million in corporate sponsorship, which came out to like $250 a person, and the paper acceptance rate went down from it was at like 28% or like 30%, went down to 21% because it's getting more competitive to publish at this conference. Yeah, so this is what I did all week. It was a lot. Monday they had tutorials, but I didn't pay for those. So I instead volunteered at WIML, which is Women in Machine Learning, where anyone can attend or volunteer, but only women are allowed to present their research there. Beneficial experience. And actually, the person I roomed with while I was out there, she presented her poster at WIML. And then just kind of walked around, did some networking, and John Platt, who's the chief scientist at Google AI, I think, or Google, I don't know, talked about the future of energy and how they're using machine learning to get the entire planet, planet's energy consumption up to the U.S.'s energy consumption within the next 100 years. And they want to do that because they've noticed that energy consumption is like a necessary ingredient for quality of life. So the idea is to get everyone to that energy consumption so that we can have a chance in 100 years of having everyone with the same quality of life as currently is the case in America. And they were using machine learning to, it was nuclear fusion was like their bet. And they're using machine learning to guide nuclear fusion experiments to hopefully get to sustainable fusion faster. And it was really interesting. The video is online, and I'm going to link to all the videos, or at least all the invited talks and keynotes. There's a repository at the end of this that has links to everything. So that was Monday. Tuesday, Brendan Frey is the founder of Deep Genomics, which is an AI and genetics company. He gave his talk. The thing that I remember most from it was that they have cloud laboratories, apparently, where geneticists can write code, ship that code to the cloud, and this cloud has like a physical laboratory with robots, and the code gets executed on these robots, and then those robots carry out the experiments that they would do if they had the materials in front of them. Analyzes the results, ships it back, and you do this, and you press execute, and a couple hours later, the results of your experiment come back, and they're doing this to like streamline genetic research, make it as quickly as possible so they can iterate. And then, yeah, Tuesday, also bounced between some sessions, algorithms, optimization, and theory. Those are where all the papers that have been accepted to the conference, they get talked about. They have like 5-minute presentations or 10 or 15 minutes or whatever. And then I did catch that talk that Andrew just talked about, Kate Crawford, on bias and ML. She is like the leading researcher in this area of research. She was pretty much like I think the one who discovered it in these large-scale machine learning systems. And so she's with Microsoft Research and NYU. And I think if you're interested in that, she's the one to go to. Also, Hannah Wallach is a good one too. She does computational social science and uses machine learning for that. And she's very active in WIML as well. So yeah, then Wednesday, mostly went to deep learning and reinforcement learning sessions, and Peter Beal on deep learning for robotics, which I'll get into in a minute. Then Thursday, went to a deep learning session in the morning, and then they had the symposia, which is where they split off into separate tracks for different topics, and you kind of go to the one that you're interested in. I went to the deep reinforcement learning symposium because that's what I'm interested in as far as research goes, and that was from like noon to like 9 p.m. or something. And I'll be talking about that. And then Friday and Saturday are the workshops. Those aren't included in the main conference, but I did attend those. And Friday I went to mostly application stuff. So I went to machine learning for computer security, which is pretty cool, and machine learning for healthcare for like the afternoon. And both were really interesting. I'm free to talk about all this stuff afterwards. And then Saturday I checked out hierarchical reinforcement learning, but didn't really get into it. I just don't know too much about it. So I went over to meta learning and learned more about that, which was pretty impactful for me. I think that was my favorite part of the conference. So these are the three that I'm going to be talking about. And they're all centered around deep reinforcement learning. And oh, I'm sorry, this is going to be an advanced talk. I had that kind of labeled. There's really no way to get state-of-the-art research and to compactify it into like a beginner's level talk. So if you have any questions, please ask, and I hope we'll get through this. So reinforcement learning, briefly. There's a lot here, and this is like the main thing that I study. And this is a mathematical definition of it, but really what it boils down to is you have an agent, which could be any of us or an AI, in an environment. And that environment could be as simple as a game screen, or it could be as complex as the universe in the real world. And this is there's some philosophical assumptions at play here, but they're more like inductive biases that we code into this framework mathematically so that we can learn. These assumptions are that you have states. So right now we're in a state, and right now we're in a state, and at each time step we're in a different state, right? The position of my arms and the position of my legs and all that is a different state in this room, right? And all of you being in this room, your position contributes to that state information. And the environment is always in one state at one time, and it moves through successive states in successive time steps. And then the agent is in that state, and it has to recognize that state and then choose which action to take. And choosing that action, the environment then takes that action in, transitions states, and produces a reward. So the goal here for the agent is to maximize cumulative reward. And this is all defined mathematically in your task. And how you choose how you choose to represent the state or the action, and how you choose to calculate that reward is going to be very important for whatever you want to learn. So like some examples of this are playing Atari, right? We want a computer to play Atari. The states here are the game screens. It's playing Breakout right now. And so I guess the state where the ball is, where the paddle is, and the layout of the bricks up there, that all is considered the state of this environment. And then the score of the Atari, that the Atari game system creates, that is the reward. And the goal here is for the computer to move that joystick digitally, choose actions. Those are actions, right? It chooses to go left or right. And the goal is to choose those actions so that it gets the highest reward for the game. And this is another one in robotics where we have a robot dog in a simulated environment. The state of this environment is, the physics of the real world and the position of the dog and the velocity of its moving parts, etc. And the reward is maybe how far it has sprinted thus far in the episode, in the current frame. And the actions it can take are, of course, to move its limbs and to try to walk or run. And then you can teach this simulated robotic dog to run around in this simulated environment that they've created. And this is not just for robots and games. You can also consider, let's say, the stock market as an environment, and an agent as the trader. And the different actions you would take would be, I want to buy this stock here and sell this stock there. And the goal is to maximize the value of my portfolio over time, right? And so, like in general, this reinforcement learning environment setup is extremely general, and it fits a lot of different applications where you can interact with an environment to generate new data and learn from it. And we're finding more and more that this is very useful for a large variety of tasks. So to break it down a little bit, an agent is made up of two things. Well, it only really needs one, but two become useful. We have pi, the policy. That's a function from states to actions. So knowing that I'm here in this room, what action do I want to take to get closer to my goal? Like if I want to walk out that door, I need to know that somehow to go that way instead of that way. And the policy is what mathematically and computationally provides that information. And then you have Q. That's the value function or the action value function. And it's some estimate of cumulative reward, right? Let's say if I'm all the way over there and I'm trying to get to that door over there, I have a long way to go. So my estimate for cumulative reward is not going to be that great, right? But as I move closer to that door, my estimate for cumulative reward is going to go up because I'm closer to the door, and that's where I'm going to get all my reward. So, and it does this by kind of averaging over all the possible outcomes from my current state, and that's ideal, right? Usually all these different outcomes, there's far too many to actually compute that average. So we have to approximate it somehow. Although that value function is not strictly necessary to do reinforcement learning. The policy function fully defines the agent. All you need to do if you're an agent is have some way of choosing what to do next. And if you're really good at doing that, who cares if you know how good it is being in this state? But in practice, the value function can be helpful to kind of guide that learning, and we'll talk about that in a second. So the goal, like I said, is to maximize cumulative reward over time. And rephrasing that with this new terminology, the goal is now to find an optimal policy. That means to find a policy that will lead to that maximum cumulative reward over time. So there's 3 strategies to doing this. We can learn the policy directly, which was choosing the actions, right? We can learn the value function and then derive the policy from that, which means if all we care about is the value function and how far away I am from that door, I can look at all my possible actions and then just choose the one that leads to the highest value. And that, theoretically, as long as my value function is strong, will get me to that place of maximum reward that I want to. Or we can learn both simultaneously. And in that case, we use that value function to improve the policy as we're doing all this. And I think I forgot to mention that the policy function, the value function, they can be closed form algebraic. So they can just be like, a mathematical expression of your state. For instance, distance to the door. I could calculate the Euclidean distance from me to that door and use that as my value function, perhaps. Or you could have, in general, that doesn't work for all problems though, right? There are more complex environments where that's not gonna work. So what we do is we approximate that function that we want with a linear model, a neural network. There are a lot of different ways to do this, but yeah, so the policy, the value function, those can usually, in practice, will be some kind of models that we're learning from data by interacting with the environment. And these are some algorithms for each of those categories. I'm not really going to go too much into them because they're not really that important to what I'm trying to say. But I just put them there so you can look them up if you're interested. And later, and these slides, again, will all be online. Oh, so these algorithms, especially like the first ones and the second ones in these lists, those are like the shallow versions, not using neural networks. And those, for a lot of those, you can prove that if everything's well defined, especially your environment, and you've set everything up correctly, these algorithms will lead to an optimal policy eventually. Which means that no matter what problem you throw at it, eventually it'll learn to maximize that reward. A lot of time, that's in theory though, and a lot of times we don't have the time or the data, or sometimes it's impractical and it's not actually going to happen like in this universe, right? So and a lot of times that's because of like high dimensionality or something called the credit assignment problem, which I won't go too much into, but essentially the reason people are using deep neural networks for this in particular is because some of those problems can be mitigated by using them. And although when you do that, you lose the guarantee of optimality, in practice, they outperform these other methods pretty extensively. You can do things that were never possible before, as far as we know. So what's the problem if that's the case, right? Well, there are stability concerns. Like usually when you train an algorithm, you want it to converge to that optimal solution and not diverge once it's gotten there. But a lot of times that'll happen for these kinds of algorithms. And when you're using neural networks. And there's lots of research that's gone into addressing this, but it's an ongoing process and it requires a lot of tricks. But there are ways to do that. So that's not the most pressing concern. There are other technical problems that we'll get into now, though. Exploration versus exploitation is one that we'll get into, and then reproducibility and open problems for the field in general that haven't been solved yet, we'll get into later. So what is exploration versus exploitation? It's the idea that sometimes a suboptimal choice now can lead to more optimal strategies later on. For example, you have this guy. In the literature, this guy's known as the multi-armed bandit. For some reason, they always represent him as an octopus who looks like that. But the idea is like this octopus bandit, whatever, is in a casino and he's playing all these slots with all of his different arms. And maybe that first machine on the left is programmed so that every time you put a coin in, it gives you a coin out, right? Which isn't that great, but it's a reward every time. And then the next one over has like a 50% chance of giving you 3 coins. So between those two, we want to hit that second one because we're going to get more coins from that machine. And then, maybe later on, maybe there's this one special machine that gives you $1 billion with a 1% chance. And obviously, if we know that, like that's the one we're going to take, right? Our expected return from that is 1% times 1 billion, which is a lot of money. But the problem here in reinforcement learning is that we don't know the probabilities for each of these slot machines. We don't know which one's the $1 billion one or the $1 one. And we have to figure it out through trial and error, through pulling the levers and seeing what happens. And so if you're just naively doing this, and you're just trying to, based on what is happening, you're trying to get the most reward, you're maybe going to hit that first one and say, oh, I get a reward every time. Why am I even going to try these other ones? Or if you try them, maybe you're going to say, oh, nothing happened. I'm just going to keep hitting this one. When in reality, the optimal choice is all the way down the row and is only going to pay out 1 every 100 times. But so exploration is needed in order to get to that optimal choice. And there are a lot of strategies to doing this. The most common form is called action space noise. It's basically where I have an idea of how well I'm going to do, and usually I want to pick the best, right? Like for the door, usually I know stepping in this direction is going to get me closer to the door, and that's the greedy option. But in order to explore, every time I say, well, that's the best way to go, but maybe for 5% of the time, I'm just going to step over here just to see what happens. And that's how you explore. You just randomly choose a different action than you would have taken before. That's action space noise, and it's very common, and it is generally how it's done. But there are problems with this, right? The noise is not correlated over time throughout the episode. So I could be right in front of the door, and all of a sudden I take an exploratory move, and I've just right there. And so, generally, maybe I'd want to explore more while I'm over here, and then once I get closer, I say, all right, I kind of see what's going on. I'm going to keep going and forget this exploration stuff. What? We're assuming the door's open here. But, and I'll actually get into tasks later where you have multiple like subtasks going on. I'll mention that later. But
so are you kind of leading down the road to something like knowledge gradients here, or what?
I'm not sure what you're referring to, but
it's a way of comparing exploration versus exploitation and trying to make the best guess based on what the potential reward would be for the next move. The predictive.
Yeah, there.
Yeah, in particular, you take a look at if there is a prediction that you make about, say, moving to the door, that there are some things like what you just said here, where the first machine always gives you a payout, but the payouts are not optimal. And then you go, so you know what the reward is, and you know what the variance or the uncertainty is in that. And in other cases, you have things that may not be as high as an immediate score, but it has a higher uncertainty, and so you go for the one that has a higher uncertainty because you can explore that space more.
Yeah, so that's like a formal way of looking at. So uncertainty estimation is one way of dealing with exploration. The standard algorithm for doing that, I think, is called like upper confidence bound, or the UCB algorithm. That's like that's like more classical stuff. Unfortunately, that's not always possible to do, and I think that's a little bit off topic to get into the weeds there, but we can talk about it afterwards. So the first problem was that noise is uncorrelated, right? I could be right in front of the door and all of a sudden choose an exploratory action, when there's really no need to. And maybe I want to be able to control when to be noisy or explore. And then the other part is that the noise is state independent. And that's a similar problem. So for those states over there, that's when I don't want to explore. But for those states over here, I don't know how to get to the door yet. So maybe that's when I do want to explore. But there are like, they're related problems, but technically different. And one of the talks that I saw at NIPS was getting around this, or trying to solve these two problems. It's called parameter noise, and it's basically you introduce noise into the parameters of your policy or value networks, or whatever parametric model that you're using. And so generally we have, for each weight in the neural network, we have a single value, and that's going to determine how the network does its job. Here, instead of having that single value, we're going to impose a distribution over that value, generally a normal distribution. And then we're going to sample from that distribution, and then we're going to call that the weight or the parameter. And we're going to do this for every parameter in the network. In general, that could be anywhere from thousands to millions of parameters. But what it does is that the noise is now state dependent, because we're inserting our state into the beginning of the network, and we've already chosen the parameters. We've already sampled them from these distributions, so we have a single network, and we're just going to pass it through deterministically. And every time we do that with those same parameters that we've sampled, we're going to get the same action, whether it's exploratory or not. The action is now state dependent as opposed to being state independent. And then, in addition, because we're sampling from a distribution, we can choose when we sample from that distribution, so that we can hold the noise constant when we want to. When we want to generate behavior that's similarly exploratory or not, we can do that at will. So those are the advantages to using parameter space noise for exploration. There are two methods that have recently come out about this. There's the learned method, which came out of DeepMind. That's basically where you learn both of these parameters of the distribution with gradient descent and backpropagation, like you would in a normal neural network. And then there's also adaptive, because for that, you're basically doubling the size of your network, and that, from an optimization perspective, is very computationally costly. So there might be a hack that we can do to get around that, and that's what adaptive noise attempts to do. You learn the center of the distribution and then adapt the scale or the spread of the distribution. Adapt it dynamically based on some measure of how noisy that network is, as opposed to the regular unnoised network. And that one came out of OpenAI. I had a chance to speak to one of the authors of that paper while I was there. And the problem here is that those two papers, they came out around the same time, I'm assuming. And they're attacking the same thing with basically the same solution, just a little bit of a different technical implementation. But they got completely different results on these same tasks. They'd be playing this game in Atari, and one of them would do way better than is normal for a computer to do, and then one of them would do way worse. And then there'd be some where they had similarly good or bad performance, but then others where there was no correlation there. So the question was, like, does this actually work or not, and which one's better and stuff. Which leads me to this talk, which was one of the keynotes for the Deep Reinforcement Learning Symposium. Reproducibility in deep reinforcement learning is actually a huge problem, despite it being a very large field in AI right now. So like the experiment that they ran was they took two competing reinforcement learning algorithms that had been tested on the same task, and in the papers that presented them, both claimed that their performance was superior with statistical significance. But the only difference between the two implementations, or at least they implemented both of these algorithms in the same code base, and the only thing they changed was the random seed. And that's what caused the difference, which means that these results weren't actually robust to random chance. And that's a huge issue, because scientists don't always report their random seeds. They don't always report, and if that's the only thing they don't report, you've really gotten lucky, because there's a ton of things reported in these papers, and it's very hard to reproduce a lot of this AI research. And there's also concerns about like, this lab has all this computational power, but no one else in the world has that kind of computational power. So how could anyone possibly reproduce this result? Particularly with like AlphaGo that came up. And one of the creators of AlphaGo, David Silver, then responded to that and was like, well, should we just not publish? Is that what you're saying? And it's just a good dialogue. And if you're interested in that, deep reinforcement learning that matters is the paper that this talk was based on, I think. And Test of Time talk was like, made a huge splash that week. Basically like analogizing like deep learning to alchemy. So yeah, check it out. I have links to all this stuff in there, and it's really interesting stuff. So in relation to this, back to the parameter space noise, before I even like went to NIPS, I had started playing around with these and implemented both of these different solutions for parameter space noise in the same code base. So the whole idea was to control, able to see and stuff, to focus on reproducibility. And I'm still working on it. I have like half of it done. And I have the framework and I have like the DQ network stuff, but I'm still working on the policy stuff. So if anyone's interested, I could use some help, whether that's like compute time or coding. And a link's there if you'll check it out. Talking to the author of the OpenAI paper, he was like, hey, and he was talking about it. We were getting into it, and he was like, but I mean, really, this is parameter space noise. Like, is it really going to solve exploration? No. And I had to agree, and because it is still fairly naive. It's just like transferring the randomness from one place to another, really. So there is something that needs to be more sophisticated in order to do this. And one thing was presented at this conference called Deep Exploration via Randomized Value Functions. It came out of Stanford in Ben Van Roy's lab, and it was Ian Osband's thesis. And there's a video here of him presenting that. I'm not going to go into it because I'm still having a hard time digesting it. But yeah, so now deep learning for robotics. This is Peter Beal. He's like one of the most incredible like researchers in the world right now. I think his like average paper time is like he has a paper coming out like every week or something, and like most scientists, publish like one paper a year, 2 papers a year. A lot. He has, yeah, he has a lot. I mean, well, he worked at OpenAI, and he also was like one of the head AI researchers at UC Berkeley, and so he has a lot of students, and it's the best school in the world for this kind of research. So yeah, he has that going for him. But he presented what he sees as 6 open problems with this kind of research, specifically for robotics, but it also applies to just deep reinforcement learning in general. And I'm going to go through those a little bit. What he wants is faster reinforcement learning, because a lot of these, for example, the ones that play Atari, right? A human can pick up Atari and maybe in an hour achieve like pretty strong performance, right? And in order for a computer to match that, it takes probably 100 hours or 200 hours of training, and that's not satisfactory, right? We want robots that learn as quickly as us or more quickly, even if these robots or AIs can learn superhuman performance. If it takes them 40 days, is that really practical? Are we going to retrain these AIs on all these different tasks for 40 days out? So we need, and this is called sample efficiency in the literature, and so we need faster reinforcement learning. Long horizon reasoning. This is what you were talking about. Imagine a task where we have a robot and its job is to get your child to school on time. So there's a lot of tasks involved with that, right? You have to wake the child up, make sure that it gets up, cook it breakfast maybe, make sure it goes, takes a shower, gets changed, gets ready, gets its books, all this stuff. It's packed, it's ready to go, it's eaten, and then you got to get out the door onto the bus on time. And that's a long series of different tasks with different goals, but they all have to be coordinated in a way that the overall goal is satisfied. And that is really hard. That's what hierarchical reinforcement learning attempts to do. But we'll get in, I'll mention that a little bit. Taskability, we want to be able to transfer between tasks pretty quickly and pretty easily. You know, we want a computer that can play chess to be able to play Go. We want a robot that can pick objects up. We want that robot to be able to place it on a shelf, which are like basic tasks that humans do very easily, but we have a hard time doing with AI so far. Then we have lifelong learning. For example, if you want a robot in a warehouse to know where everything is and be able to pick up stuff and put it where you need it, you know, and that can be done, right? Theoretically, with enough resources and training time and all that stuff. But what happens when, you know, we get a new shelving system and all of a sudden all these new parts are just like the parts that were there in this shelf are now in that shelf, and there was a whole reorganization of the warehouse. Then you just drop this robot in and it had specific information attached to the layout of the shelving, and all of that's gone now. And how do we make sure that a robot, and you know, that's kind of a dramatic example, but maybe even little tweaks to the environment over time can build up, and then the robot can lose its efficiency if we're not taking care of that. So that's called lifelong learning. And and so he proposed these open problems and then proposed research directions that his students and teams have been working on, and I'm going to go into that. The fifth was leverage simulation. This means it's expensive to carry out these experiments and to train these AIs. And we want to be able to train them in simulated environments and then deploy them in the real world, right? That seems very optimal because simulated environments happen very quickly and human environments happen very slowly, relatively speaking. And that's actually, there's something called the reality gap that's hard to bridge. And then the last one was maximize signal extracted from the real world. So where situations, when we're in situations where, simulation is probably not going to get us there, or there are legal restrictions as to why that would be the case, or just, ethical or logistical problems, and we need the real world, we want to be able to maximize the signal that we get from that real world. These are all the proposed directions. I'm not really going to get into each of them, but I had them up here so that you can take a look if you want to. This is what I'm going to focus on because it's shared between three of these. It seems like a very promising direction for this kind of research. And I attended the workshop for it on Saturday. So meta learning. This is a picture I took at the workshop. This was a panel they had at the end of it. Really great talk. So the first part of this whole panel was like, there is no concrete mathematical definition for meta learning. And one of the questions was like, do we need that? And what is it? And everyone kind of agreed they didn't really know. And eventually one of the guys on the panel was just like, we're not even philosophers. Why are we even talking about this? All we need to do is like create it. We don't need to define it. And I thought that was kind of funny just because that's kind of a philosophical statement in and of itself. But basically what these are, and just colloquially, they are a collection of algorithms that learn to learn. So neural networks and random forests and SVMs, they are algorithms that learn tasks, right? Single tasks, though. They learn to get good at a specific thing, like classifying images or sentiment or whatever else you want. And but we don't have algorithms that can learn how to do all of those like at the same time, right? We don't have an algorithm that we can train that can then go and learn how to do each of those without us like needing to interfere at all. And that's what meta learning attempts to do. It's basically learning the way humans do, right? We learn how to learn, and then we learn all these different skills as we grow up. So this research actually does go back to the 90s, but it was very sparse back then, and it's kind of picked up steam recently. RL squared was one of the things that was presented that came out in 2016. Basically, you have a reinforcement learning algorithm tasked with training a faster like sub-reinforcement learning algorithm. And the sub-reinforcement learning algorithm actually ends up being like a recurrent neural network for technical reasons. But the idea is you train the faster reinforcement learning algorithm on a multitude of tasks, and then you can just basically deploy it on a new task that it hasn't seen, and it will learn fairly quickly, much more quickly than standard reinforcement learning. And And that, that was one of the first open problems on his list, right? Was faster reinforcement learning. Then Snail is similar, but it uses a different version of the sub algorithm there. It uses like a WaveNet kind of architecture, if any of you have heard of it, which is how Google is doing speech-to-text synthesis or text-to-speech synthesis right now. But anyways, it just gets better performance, so I thought I would put it in there. Yikes.
Are these suboptimal learning algorithms like the version of
Mancuso? What do you mean boosting?
Learners and it's basically do everything by hand.
No, I think this is something different. Boosting is kind of like ensembling models, right?
Yep.
This is like you have kind of a hierarchy of the models, where one is teaching the other and the other is learning from tasks. Yeah. Okay, and then MAML, model agnostic meta learning. This is where instead of using like reinforcement learning to train these things, you do like gradient descent. And I'll get into it actually because it's kind of a big topic. So this was probably my favorite talk of the conference. The key idea is that you want to learn parameter vector. That is a good initialization for fine tuning for many tasks, which boils down to, you have these networks, right? These models are parameters, the weights of the network that I mentioned before, the same weights that previously we were injecting noise into to get that exploration. Here, though, what we want to do is instead of training those weights to be good at one task, we want to train them to be good at many different tasks eventually. So instead of training over different data points in a single data set, you're training over multiple tasks, which can themselves each consist of its own data set. For example, there are data sets out there. There's one called Omniglot, where it's pictures of alphabet characters. And the reason this is useful is that it's split into different tasks, right? So it has certain characters that are held out that are never seen by the model. Because we have these image classification networks that can predict those characters as long as it sees enough examples of all the different characters. But what we want to do is different. We want to be able to learn or be able to predict on characters that haven't been seen at all. We want to take the letters A through L, learn from those, but then be able to guess what M, N, O, P are without ever seeing an M, an N, an O, or a P. And the way you do that is with this. Essentially, you train this loss function. I don't think it's going to mean much to anyone, but the picture is really what we're getting at. The arrows here relate to different points in parameter space, which is basically different settings of the parameters in that model. And you have these starred versions of each vector, and those are what are considered optimal for the different tasks. And we have 3 different tasks here, so we have 3 different sets of optimal vectors for each task. And obviously those aren't all in the same place because optimal is going to be different for each task that you're working with. But the idea of MAML is to find a parameter vector that is as close as possible to all 3 of them so that you can use that and quickly get to any one of the other 3. And the idea is to do that in general for a large number of tasks, especially ones that we haven't seen yet. So instead of generalizing from data to new data, we're generalizing from tasks to new tasks. It's cross-validation at a different level. So like generally you get a data set, right? You split it into training, test, validation, right? Or whatever. However you want to do your cross-validation. But all that data is the same data set. So for example, with MNIST, which is just digit classification, right? Your training set, your validation set, your test set, it's all going to have the digits 0, 1, 2, 3, 4, all the way up to 9. and images, and they're all going to be labeled, right? So you're going to be able to train on all those digits. You're going to be able to validate and test on all those digits all together. Here, it's like we're splitting the first 5 digits. That's our training set. And the second, or the next 2 digits, that's our validation set. And the final 2 digits, that's our test set. And we're saying, all right, learn how to classify 0 through 5, and then quickly learn how to do 6 and 7. And then eventually we're going to test you on 8 and 9.
Can you link to transfer learning?
Yeah, very much. Yeah, sure. Transfer learning is very related, actually. It's kind of like a special case, I think, of meta learning, where with transfer learning, you train on a single data set like ImageNet, where you have 1,000 different categories, and you train this model, and it gets really good on that data set, and then we have a new data set that may be similar, maybe different, but it's a different data set, and without fine-tuning on that new data set, the performance of the model is not likely to be that great. But you can transfer it over and fine-tune it to that particular task and get very good performance because you've pre-trained it on the old data set. That is, so that's similar, right? That's taking one data set or one model that's been trained on one and then fine-tuning it towards another. The difference here is that we want to do that for a large variety of tasks. That was one task to one new task. Here we want to train on a bunch of tasks and then be able to generalize to a bunch of tasks quickly for all of them. Whereas with transfer learning, you are pretty much transferring to that one task, and it's going to take some time. And with transfer learning, it's dependent on, like, you need to train on a data set that is going to be good to transfer from. Here, you'd want to train on tasks that will be good to transfer from. And the main difference, I think, is that with transfer learning, it's all in supervised learning, generally, right? Potentially in unsupervised learning. I actually haven't seen that done, but potentially, I don't know. Here, though, this is a fully general learner. It's not exclusive to supervised learning or unsupervised learning. It can be done for reinforcement learning, too. And this can approximate any learning algorithm in theory. If you're at the first talk we had, I mentioned that neural networks can approximate any function, right? This is different. A neural net is a learning algorithm that can approximate a function. This is a learning algorithm that can approximate other learning algorithms. So it can approximate a neural net, or a support vector machine, or a random forest, or a learning algorithm that we don't actually have a mathematical description for. That's what I find so interesting about it and so fascinating, is that you can potentially get learn new models that haven't been done before. So the results here are actually pretty good too. They did one-shot visual imitation learning for robotic grasping. Basically, they took a video of themselves doing a task, like a grasping task, picking up that block out of all of these objects. Only did that once, showed the robot the video of the human doing it, and then the robot went and did it. It only needed one example, and was able to do that. And in general, in the past, those kinds of tasks require lots and lots and lots of trials. And then it also got state-of-the-art performance on one-shot image classification, which is a similar thing. You know, you show it one picture of something, and then it's able to classify that in the future. So I train it on 0 through 5. I show it a 6. It learns that 6, and then anytime I show it a 6 in the future, it'll guess it correctly.
Or even just variations of a 6 also?
Yes, yeah, no, variation of a 6. Not that exact image, but 6 written in cursive for a different handwriting style. Or
that case, you have the 1 through 5 version.
What do you mean?
You had the 1 through 5 version.
You have to, well, so for model agnostic meta learning, you have to have a separate set of tasks that you train on. And then in test time, you feed it one image, it learns that image, and then it can guess on the rest. Yes, you would show it, yeah, in general, this model, that's how it works, yeah. Yeah, so, I mean, so far we don't have any method of doing that without some kind of training. What this does is allows you to transfer from maybe related, maybe unrelated tasks to new tasks. Yeah, well, that's what we need. And then, yeah. And then, so like I said, this also can be used for reinforcement learning to speed up that, get that fast RL. But the other two techniques I mentioned before tend to outperform it so far. And what I think is important about this one is that it's fully general, like I said. And then mastering games with deep reinforcement learning. That was David Silver. He's the lead researcher at DeepMind and the creator of AlphaGo. But there's too much to cover right now. So that's like that's a long, yeah, that's a really long topic. And what I'm hoping to do is have a special event where we talk about this, because it's like probably my favorite story from like AI in the past, 10 years or whatever. And it's a really fascinating story. They just came out with a documentary about it. So I was hoping we would get to screen that and then talk about it and maybe learn about it. So we'll get into that. Stay tuned. And if you're interested about NIPS and a lot of the stuff, I mean, I only covered, what I focused on. There's a ton more that I saw and that I didn't see. There's this repository on GitHub. It has links to videos if they're available online and slides if they're not. And if there's not, then it just gives you the title of the talk and you can find the author and do some digging into research they've done if you're interested. David Abell's notes are also really good. It kind of is similar to what I just did, but from his perspective and the stuff that he saw. And then there's more instructions about how you can find out more about each session and the different papers and topics that were covered. And these slides will be online too. All these links, you'll be able to click through them once I put it on GitHub in like tonight or tomorrow. So that's it. Yeah, the link to GitHub is in the About section of the Meetup group page. Basically, like when you land on our group page, you know what? I can actually show you. I do this. So this is, this is our Meetup page, right? You have the next meetup still up top, and then it says what we're about. And you click read more. And down here, that. So then you go to GitHub. Here we are in Hub. And these are slides from our last two meetings. And there's also this learning document that I put together because that's a question we've gotten asked a lot. And I kind of just went through the stuff that I knew about and how I did it and all that. So that's there. And this will be contributed fairly frequently. And also, if you have issues with the group or that you want to see presented or that you want to present, you can either email me or file an issue on GitHub. And if you want to actually contribute to this repository, anything else, you can file a pull request. And we don't have any yet, but I'm hoping we will. So yeah, that's basically it. And if anyone has any questions, I'll do those now. Yeah. Yeah, it can be. It depends on how you're representing your state. So, like for example, with the Atari, you're representing the state by the game screen, which is what a human would see. And in general, like when you have images like that, you want to take advantage of all the spatial information. RNNs tend to take advantage of temporal information, like things that happen over time, whereas CNNs, convolutional neural networks, focus on like more of the geometry of what's right in front of you. And so yeah, but in general, like yeah, using or LSTM is a kind of RNN, and LSTMs can be used to learn long-term like dependencies and strategies, and it is used in reinforcement learning pretty frequently.
That's really by that, I'm thinking learning in the sense of
No, it probably couldn't. I don't know. Like that's so to learn how to speak a language. There's multiple like subtasks. Like I said, first of all, you need to be able to speak, right? So you need to be able to take text and turn it into audio, and there are models that can do that, but they are different models and than the models that actually tell you what words to say. And those we have models for that too. So maybe if you put them together, you could think of something. But then on top of all that, you have to think about like, language is language, and speaking a language grammatically correctly is one thing, but developing the concepts and then attaching all those words to those concepts and then having a conversation conceptually is quite another thing. And that's something that we're not even close to solving. And if we had solved that in my lifetime, I would be very happy and very shocked.
let's say
This technique in particular? No. No. So, I mean, yeah, like I said, we're not even close to there. Maybe one day we will be. I don't know. I'm not good at forecasting, but yeah. Actually, there's one guy I had lunch with at NIPS. His name's Miles Brundage, and every year so far for the past 2 years, he's written up a document giving his forecasts for how AI research is going to go for the next year and saying, like, these are the milestones we're going to hit. These are the ones we're not. And he does this for most of the major fields of AI. And then at the end of the year, he sees how he did, and he actually does like statistical evaluations. He like looks into the forecasting literature and like bases his analysis on like previous work that's been done, and like kind of like critiques himself, and he's like kind of harsh on himself about it. But I linked to it. I think if I don't, I'll post it on the meetup group. But yeah, it's just kind of like an interesting thing that he does. But with Atari specifically, he's actually very good. He's like I think most of the predictions that he made about Atari that came true this year. But that's because I think that's because like Atari is just kind of a special case where it's easier to predict. And I think he mentioned this too, where like other things where he doesn't have as much experience or a bit more open-ended, his predictions were much farther off. And he has, like I said, he has this whole article like critiquing himself and seeing how he did and seeing what he can do better and all that. It's like an interesting meta kind of.
Yeah, exactly.
Yeah. So I guess, are there any more questions? Yeah.
I had sent yesterday a comment.
Yeah, I saw that.
With the link to the Gary Marcus thing about what deep learning is and what it's good at and what it's not good at.
Mm-hmm.
He linked beyond Lacoon saying maybe backpropagation is exhaustive and look at the next thing. And I don't know, do you have a comment on that? Or too big for stuff like that?
Definitely. I have a few comments on what he wrote. The first is that what I noticed when I was reading it is that a lot of his criticisms that he leveled against neural networks are better leveled against supervised learning in general. So these, he called it neural networks, but you could say the same for linear models so that was the first thing. The second thing, though, I mean, he did have a strong point in that, like, supervised learning and neural networks in particular, even though they are this potentially better form of supervised learning for a lot of things, not everything. Like, even then, like, that's not going to be enough, right? And I don't think anyone in the AI research community is actually legitimately thinking that. So I'm not sure who he was, like, arguing for, because the only people who are going to read it are, like, people who are interested in that, and if they already don't believe it. I don't know. But so.
Well, I think he's arguing for it's helpful to understand what technologies we have, how far they can go, and they can't do everything, and therefore we've made a lot of progress, but there are things we don't know how to do yet. We don't know how we're going to do it.
Yeah, I guess it reminded me of one thing that was said at the meta learning workshop. It was, oh man, it was said by the guy holding the microphone in that picture, second from the right, Oriol Vinyals. He's like one of the senior researchers at DeepMind, and someone asked him, kind of similar to what you asked, right? Do you think meta learning could potentially be something that gets us to general intelligence? And if so, do you see any benefit to trying to incorporate evolutionary strategies into it, right? Like, that's how human intelligence evolved, right? So maybe there's something there. And his response basically was, I mean, who knows if meta learning is going to be a thing, but what I do know is that human intelligence had the benefit of, 100 billion humans who've lived, each of them with more compute power than, like 40 times more compute power than computer that we have has. Actually way more than 40. 40 times 60, so 240. But so and that's just one human mind, and there's 100 billion human minds over the course of human history that have contributed to the evolution of intelligence. So all the compute power in the world could not get us there, and all the compute power for the next 50 years may not get us there. So either we're not going to get there, or we're going to have to create algorithms that can get there much more efficiently. And so, yes, deep learning is probably not going to get us there, but yeah. So, anything else? Cool. Last thing I wanted to say real quick was thanks to our sponsors, Pandata, Progressive, for hosting us. And like I said, if anyone wants to talk for the next one of these, please let me know. Issue on GitHub or email me, whatever works. I feel like there's something else, but whatever, it's a long night. So see you guys.
Fine, folks. I just want to make sure I logged out of the
Sure.
cloud.
Yeah, let me